In this video, I'll talk about kinetic molecular theory. From this name, we know it's about the motions of the molecules. But first, let's review the gas laws. A. Avogadro's law, B. Boyle's law, and C. Charles' law. The Avogadro's law tells us volume is proportional to the number of moles for gases. Boyle's law tells us the volume is proportional to 1 over pressure of the gas. Charles' law tells us volume is proportional to temperature, again for gases. Therefore, volume is proportional to Nt over P, and we can also say volume is equal to Nt over P multiplied by a constant R. That constant R is the gas constant. It's 8.31446 joule per mole per Kelvin. This is the SI unit. Or R is equal to 0.08206 liter ATM per mole K. This is one of the commonly used non-SI units. This equation can be also written as PV equals nRT, or pressure equals nRT over volume. We will prove this equation today. Pressure is equal to nRT over volume. First, gas pressure results from the collisions between gas particles and surface areas. So how do we prove this gas pressure equals nRT over V? We need to use two equations. The first equation was proposed by Newton. The momentum change of a particle, delta P, lowercase p, is equal to delta mv is equal to F times delta T. Delta T is the time period of a force being exerted to a particle. And we'll use a second equation, mvx squared equals RT over n sub a. So what's Vx? Vx is the speed of the particle in the x direction. And we need to square it. And what about this horizontal bar on top? That means the average. Let's say we have many gas particles. And this quantity is the average or mean of the speed of the particles in the x direction squared. M is the mass of the gas particle. For simplicity, we're just talking about just one type of gas particles. And then R is the gas constant, T is the temperature, N sub A is the Avogadro constant. This is a huge number. N sub A is equal to 6.02214 times 10 to the power of 23 per mole. That's the Avogadro constant. Now let's look at this diagram. We have a box here, and let's look at just one of the many gas particles. This particle has a mass m, and it's moving in a direction with a speed of v sub x. It's about to collide with this gray area A1. This A1 and this A2, they have the same surface area of A. I'm going to just use A here. And L is the distance between these two surfaces. Between A1 and A2, the distance is L. So the volume of this box is A times L. Now let's look at the derivation. Pressure is equal to F over A. F is the force. A is the surface area. But look at this picture. It shows you only one particle. In reality, there are many gas particles. Let's say we have uppercase N particles. All right, if you have one more gas, N equals 0.6.02214 times 10 to the power of 23. All right, so this is the total number of particles. And then we want to know what's the average force each particle exerts on this gray area A1. Well, very simple. It's just the average of the momentum change divided by the time period. Again, this is simply from Newton's law. Delta P is equal to F times delta T, then force is equal to delta P, the change of the momentum over delta T. So that's what this equation is about. However, not all particles are moving at the same speed, and the time duration is different for the collision of each particle, so we're just looking at the average here. What's delta P? Just imagine this particle is colliding with A1 and then bounces back in the opposite direction. What's the change of the speed? 0. But what's the change of the velocity? The velocity is directional speed. It has a direction. So if the particle moves at v sub x speed toward A1, after the collision, the particle will again move at this v sub x speed in the opposite direction. Therefore, the change of this velocity of the particle is actually 2 times vx, and the momentum change is actually 2 times v sub x. Therefore, delta P is 2 times the mass times v sub x. Again, a positive 100 meter per second and a negative 100 meter per second are different velocities. When a particle changes its direction, the moving direction, the momentum changes. All right, and then we need to compute this delta t, the time period. So what we need to know is how frequently this particle collided with A1. This particle, let's imagine it collides with A1 and then bounces back. It's going to move towards A2 at the same speed. And then another collision happens on A2, which will change the direction of the motion of the particle. It's going to move towards right again and bounce to A1. Alright, so you can just imagine it's going to bounce to A1 and then A2 and then A1 again and then A2 and A1 again, A2, A1 again. This particle will have to travel on average a 2L distance for each collision with A1. So again, one collision here, and then the particle will have to move to A2 and come back for the next collision. Therefore, this particle has to travel a 2L distance. This is 1L. 2L distance to collide with A1 again. Therefore, this delta t is simply 2L over the speed of the particle. So we replace this delta t with 2L divided by v sub x. Again, for each collision, the time period delta t is 2L over vx. The momentum change is 2m times vx. And we're about to evaluate the average of this. But first, let's combine vx and vx. It's going to be vx squared. Let's cancel this 2 with this 2. Let's move this L to the bottom because L is a constant. So by doing this simplification, the result of pressure is n. So we still have this n here, the number of particles, times the average of this m times vx squared. Again, this is vx over 1 over vx, which is vx squared. So this is what's on top. On the bottom, we have A times L. Again, A times L is going to be the volume of the box. So now let's get back to this second equation I showed you. This equation, we cannot prove this until after taking physical chemistry. So the average mvx squared is equal to RT over N sub A. So I'm going to just highlight this RT over N sub A here and replace the average mvx squared with RT over N sub A. At the same time, we look at the number of particles and realize that it's just the number of moles of particles multiplied by the Avogadro constant n sub a. So we have this n sub a on top, this n sub a on the bottom. They cancel. The result is nRT over V. So pressure is equal to nRT over V. Now we know PV equals nRT. It can be derived based on two equations. One is from Newton's law. The momentum change is equal to the force times the time period. The second equation, we cannot prove this yet, but it tells us that the average of Vx squared times mass of the particle is RT over n sub a. And then we can prove PV equals nRT, the ideal gas law. Now let's work on two example problems. First, how does the mass of the gas particle impact the pressure of the gas? Well, the answer is, well, there's no impact at all. No matter you have helium or argon. Look, argon is much heavier than helium. They have the same equation, PV equals nRT. Why? Because if you remember our derivation, at first we have mass appearing in this equation. It seems that M and P has some relationship. P is proportional to M. But in the end, because mv squared is equal to RT over n sub a, it tells us this part in total, again the average of mvx squared, does not depend on the mass. It's RT over n sub a. Alright? So over here, it does not affect our result. PV equals RT for all gases. However, the mass of the gas particle does impact its speed because, very simple, this is a constant. If the temperature is constant, mv squared is a constant. Alright, and then the heavier the gas particle, the smaller the Vx squared. Therefore, the smaller Vx is. This is a qualitative question. The larger the mass, the lower the speed. Finally, a numerical example problem. Let's calculate the pressure of 0.20 moles of gas in a milk jug at the room temperature. So basically, we just need to memorize and use a simple equation, PV equals nRT. So PV equals nRT, therefore P equals nRT over V, and then we plug in numbers. We need to make sure the units are consistent. So we have 0.08206 liter ATM per mole per Kelvin on top as the gas constant. And then on the bottom, we should use 3.8 liters instead of a gallon or 0.0038 cubic meter. This is to ensure this volume unit L, liter, and this volume unit, liter, cancel. When we do this, the two L's cancel. This mole and this mole to the power of -1 cancel. Kelvin to the power of -1 and Kelvin cancel. The result is simply 1.3 ATM. Finally, another qualitative question. When both pressure and volume of a gas doubles, its temperature increases. I gave you this question in the previous video. This is just a review. Again, PV equals nRT. So if pressure doubles, volume doubles, temperature quadruples. Now finally, the practice problem for you to work on. When the temperature of a gas doubles, so this T doubles, and the volume drops by 50%, how does the pressure of the gas change? The answer is in font size 2.